So that wasn't recorded. Now I'm going to introduce it to you and assume that you can read what's on the screen. The 3 steps for determining the rate law RA. First, you guess the rate law form. You can use any of these forms to get an idea of what that guess is. You run a well-designed experiment in either a batch reactor or a differential reactor, and then you check the model versus experiment. Okay, you're caught up. If you were watching the screencast, you're right where we should be. How do you check the model versus the experiment? This is the part where the math comes in. This is the part that'll be on your homework. It will probably not be, at least a rigorous analysis based, like what you're going to do on the homework won't show up on a final. I might ask you a more qualitative discussion or a qualitative question on a final, but for reasons we will see in a moment, you can't actually do this quantitatively unless you have a computer or a good calculator in front of you. There's 2 different approaches to this. One is a differential analysis, which is not related to a differential reactor. It just happens to have the same name to it. If you're going to do a differential analysis, what this means is you're going to combine your material balance plus your estimate for the rate law, so RA, but you're not going to integrate. So you do not need to be able to actually integrate your material balance either by hand or within a computer if you're going to do a differential analysis. What I mean by a differential analysis is you're going to take your experimental data, let's say you were using a batch reactor, for example, and you're going to calculate dCA dt. Right? That's usually on the left-hand side of our reactor, or sorry, not of our reactor, of our material balance. And you're going to set that equal to your rate law, for example, KCA, something like that. And then you can make a plot of these 2. So for example, if you put CA down here and dCA dt on the y-axis, the slope of those 2, so if you put your experimental data on here, let's make that blue. We'll make the other one yellow. Right, the slope of that line is proportional to the rate constant k. How do I know it's proportional to the rate constant k? Because we have the data in this form. Right, so this represents our y variable is equal to k times some slope or some independent variable like x. So this is the equation of a straight line. So if I plot dCA dt versus concentration A, I expect a straight line. I also expect no intercept. There's no intercept term on there. And the slope of that line should be my rate constant k. That can get more difficult the more complicated your rate laws are, the more plots you need in order to figure out all the various rate coefficients. But that's the essence of a differential analysis. How do I calculate dCA dt? If it's in a batch reactor, I just watch CA as a function of time and then take its derivative. So there again, I never have to actually integrate the thing. I just have to watch it as a function of time. You can do other tricks if your model is not quite as nice. So this one, for example, would be like saying RA is KCA, minus RA is KCA. That would result in something that looks like this. Oh, I forgot my negative sign sitting inside there. If your model was a little bit more complicated, if, for example, RA was KCA to the alpha, where alpha is some unknown exponent, you can do the same thing, but you can just do various tricks of linearization to make the thing look like a line. So, for example, if I were to take the log of both sides of that expression, I would have something like log of dCA dt will be equal to the log of k plus alpha times log CA. This still has a linear form, except now what goes on the y-axis is log dCA dt. ln of k represents your intercept b, and ln CA represents x. So then you've got a slope here of m, or in this case, alpha. So it still has that linear form. If I plot that on this particular scale, so if I say ln Ca down here and ln dCa dt up here, I expect this to have, again, a linear form. I'm not really worried about whether or not these lines go up or down or intercept at positive or negative or anything like that. I'm just concerned at this point about it having a linear form. That linear form then would give me information about the intercept, which is related to k, and the slope, which is related to the power, or the order of the reaction. So similar approaches, it just gets a little bit more complicated the more complicated your rate law is, but essentially they all boil down to measure the dCa dt, which usually comes from measuring something as a function of time or in a clever way with a differential reactor, and plot it as a function of something else. Hopefully you'll be able to plot it in such a way that these things are linear, but they do not need to be linear. We have other ways to determine those coefficients, even if the form ends up not being linear. You could also do the entire thing graphically, which is not an approach I particularly like, but it is covered in your book. If you want to know how to do the thing graphically, it involves drawing a line and then measuring the area by hand and then erasing the line and drawing another line and seeing if the new area is less than the old area. I don't really recommend that one. We've got computers now. What's another way that we can check the model versus experiment? If we don't want to do the differential analysis, and importantly, if we can actually integrate that material balance, we have another option. And this is the option where we'll spend most of our time. The other option is what's called an integral method. Right, so the differential method is looking at the derivative. The integral method is looking at the integral. So this one, similar to the other one, the differential, is again we combine the material balance plus the rate law that we have. Let's see, I made the other one blue, I'll make this one yellow. And the difference is that we do now integrate. We don't have to put the word do in there, but yes, we integrate this. So as an example, if we again had something like a batch reactor, and our expression was dCa dt is minus kCa, presumably we can integrate that. Most of you, I think, can integrate that. If you can't integrate it, look it up in an integral table. You would have an integral table on an exam if you ever needed it. And I can integrate the material balance with the rate law to get an explicit expression for how concentration is expected to change with time. I can then do essentially the same tricks that I would have done on the previous one. For example, if I want to linearize Ca is equal to Ca naught times e to the minus kt, I can take the log of both sides of that and get a linear expression. So I could have something like log of Ca is equal to log Ca0 minus kt. And so now this looks like y. This looks like my intercept b. The t parameter that I have over here looks like x, and my slope is k or m or something like that. So I can again linearize that form so that if I plot that data, all I have to do now is plot, for example, t over here and natural log Ca over here. I would expect that particular form to be linear. So if I plot my data like this, they ought to look like a straight line. And again, as long as you can integrate it, that's the key step, which is this step right here. As long as you can integrate it by hand, we have the statistical tools to fit any equation that comes after that. The only challenge of this method is the rate may not be one that you can easily integrate by hand. Most of them we can. We don't get particularly crazy rate laws, at least not in sort of traditional chemical engineering. If you go to like bioengineering, this can get pretty nasty. If you go to heterogeneous catalysis, that can get pretty nasty, and you can't really do the integral form. But for example, a lot of gas phase reactions that don't need catalysts, they follow this form fairly well, a power law form, that we can actually integrate. So this is one example of the integral method, or any other rate law that you can think of. As long as you can integrate it, you can apply the integral method, and they are best applied when you can get some kind of a linear form coming out on the other side. There are other kind of more specialized techniques. Your book covers them. I'll just leave a comment down here. If you look in chapters 5, section 3, and 5.4. There are other less common methods that you can try. We're not going to go over them at all, but if you're reviewing this lecture in 5 years because you need it, there's a good reference for you if you needed something else. That's things like, for example, the method of half-lives. So you dump stuff in there and you wait for its concentration to cut by half, and you can do some math similar to what we've done here and extract some sort of a coefficient. There's a method that's called excess reactants, where maybe it does require 2 molecules, really is A plus B goes to C. Well, if you dump an enormous amount of B in there, even if a little bit of B reacts with A, the concentration of B hasn't really changed very much because it's hugely in excess, and then that can simplify the rate law a little bit. So there's various tricks that you can do to make complicated expressions a little bit simpler, and those various tricks are summarized in 5.3 and 5.4. Let's see, that linear regression is a good point. This is more of a point for statistics in general. If it is possible, if it is at all possible through any mathematical trick that you can think of, you should always try to use what's called a linear regression. So we kind of have to define what linear regression is. The key point of linear regression is you're trying to fit data to something that looks like a straight line. If you can make it fit a form of a straight line, your answers will generally be much more robust and much more reliable. The reason is the process of linear regression is one that uses matrix algebra. So who's taken your linear algebra class so far? Most of you have taken linear algebra. It is a linear algebra problem in order to determine the best coefficients for something that fits a straight line. And therefore, there is no variation. If one person does a linear algebra problem and somebody else does it, and they both do it correct, you will both get exactly the same values. So linear regression is nice. If you can't get to linear regression, there's another option that's called nonlinear regression. The reason that that's less valuable is because it requires an initial guess. If one person provides an initial guess that's somewhat different from another person's initial guess, you can end up with different, what would be considered optimal responses. The reason that you have these two variations, do we want to do nonlinear right now? Well, I've already talked about linear regression. Let's talk about linear regression. So for example, we'll come back to nonlinear regression in a minute. Let's say that you have the reaction A goes to B. And we're not worried about whether or not this thing is elementary or not, but somebody's going to propose, or you're going to propose, several different rate laws, and you would like to evaluate each one and see which one is the best fit for your particular data. There are a couple of different ways that you could do that. You could say RA is equal to minus K. This is called a zero order. I think we had briefly talked about orders of rate laws when we had just started introducing rate laws. So there's no dependence whatsoever on concentration. It just simply proceeds at a constant rate. Not very many reactions work like that. But let's say you wanted to investigate it anyway. That would be one option. You could also say that RA is equal to, wait, there's a double negative sign there. There should only be one. There we go. Whoa, that's even worse. You could say RA is equal to KCA. So this is our first order reaction. Or you could say something like RA is KCA squared. This would be considered a second order. The only one that's elementary there is the one that's in the middle, but for the purposes of determining a rate law, we don't really care if it's elementary or not. For example, you could propose that it's elementary, which in this case would be first order, but you would still have to end up checking the data to see if it actually is first order or not, which is why I said when I think we first introduced elementary reactions, that was an assumption. The assumption was that some reactions will follow an elementary rate law. It need not be the case. The way that you check it is by doing exactly what we're going to describe right now. Ideally, we would like to be able to determine whether or not each one of these are the case, and if they are, what their coefficients are, by using what's called linear regression. If we're going to do linear regression, what that means is we need to represent the dependent variable as a linear function of the independent variable, which is exactly what we were doing back here, right? Every time we were writing y is equal to some linear function of x, we were writing this in a linear fashion. The independent variable is almost always time. The dependent variable is concentration Ca, because we're going to work in batch reactors for everything. So we'll add this as taking place in a batch reactor. So if it takes place in a batch reactor, the equation that we have to solve each time is dCA dt will be equal to Ra, and then we have to integrate that form. There's going to be different ways that we can rearrange the resulting expressions in order to get straight lines. So for example, let's look at, what color did I use up here? Zero order. If we look at a zero order reaction, we have dCA dt is equal to minus k. If we integrate that, we end up with Ca minus Ca0 is equal to minus kt. We could rearrange that if we want in order to get Ca is equal to Ca0 minus kt. And we now have that in a linear form, right? We know that if we plot y being Ca as a function of t as our x value, then our slope will be minus k, and our intercept will be Ca0. So this predicts that if something were to follow a zero order rate, and I were to plot t here and Ca here, I would expect this to be data along a straight line. If I plot Ca as a function of time and I don't get a straight line, the conclusion is that this is probably not a zero order reaction. It's not well represented by a zero order reaction. So that was our first one, the zero order. I'm going to do the first order one as well, and then I'll leave the second order one for you. The first order one, we have to solve the same material balance, so dCA dt, except now it'll be equal to minus kCa. And we actually already solved this one. If you look up in your notes, we had already solved this one. This looks like ln Ca, let's go back one. If you wanted it nonlinear, it would look like this. E to the minus kt, and then you can linearize both sides by taking the log and get ln Ca0 minus kt. So we already saw that expression before. This suggests that if we were to plot ln of Ca as our y-axis and time as our x-axis, then our slope would be minus k, and our intercept would be ln Ca0. So what this suggests is if you were given that experimental data from a batch reactor, and you put t on the x-axis and ln Ca on the y-axis, you would then expect this to be a straight line. If it's not a straight line, then that again suggests you don't have the right rate law. So you need to go pick another rate law. About the only other one that we do is the second order rate law. At least the only other one that we do for things that we can get these nice closed form solutions for. We'll look at a more general one here in a minute for the nonlinear one. The second order rate law, I'm not going to give you the form of that, but I am going to tell you what should be plotted. So what you should do in between now and whenever you do the homework, do exactly that integral process, rearrange it so that it's in a straight line. If you were to plot the reciprocal of concentration, so 1 over Ca as a function of time, if you were to do that, then we would expect a straight line on this plot. Sorry, I think that straight line is actually going down. Again, it doesn't, you will figure out whether or not it goes up or down pretty quickly. No, wait, Ca is getting smaller. Yeah, it should have been going up. I was right the first time. You can sketch these data points any way you want. They're just a sketch. The key point is that if you were to sketch them on this particular axis, they should give you a straight line. You'll find out very quickly when you sketch it whether or not that line goes up or that line goes down. I'm not really worried about it right now. But at any rate, if I do a plot of 1 over Ca as a function of time, and I get a straight line, great, I've probably got a second order reaction, and I can go ahead and get the slope and the intercept from that and get information about K, or Ca0 if I want to. These work just fine. Has everybody used either Excel or Google Sheets before? Like you're at least familiar with spreadsheet operations? If you're not, come see me. I love Excel. It's a great program. Has everybody plotted something and right-clicked and said add trend line? Perfect. You've all done linear regression before. If you've never done something like that, please, I am more than happy to go over it, but I have found that almost everyone has done it for one reason or another by the time they get here. The feature that you're looking for in any spreadsheet calculator is a function that's called add trend line. So pick your favorite spreadsheet operator or spreadsheet program that you prefer. Google it and say, you know, Microsoft Excel add trend line. You will get a dozen different examples of how to add a trend line. All it does is fit a straight line to whatever the data is that you have, and it'll tell you what the slope and the intercept are. We're not going to dig very deep into linear regression. We'll have an example potentially tomorrow of nonlinear regression that usually can't be done inside Excel or like Google Sheets. But all of the examples, certainly all of the homework problems, you can get through all the homework problems that require this using the add trend line function from any of the spreadsheet operators. So either Google around for it or please come see me. I'm happy to talk about it. I'm familiar with Google Sheets and Excel. So as long as you're picking one. Oh, and what's the other one from Linux? LibreCalc, I think, is the other free open source one. I can do it in that one too. So pick one of those three and I can help you out. But these are nice. They will quickly tell you whether or not something is 0 order, first order, or second order. If they are not one of those, we do have another option, which is the one that I had mentioned a minute ago, which is the nonlinear regression part. This is the part that requires guess and check. Everybody in here, in fact, everybody in the world, if they ever solve a linear regression problem, will come up with exactly the same coefficients, assuming they were all doing it correctly. The other option is, what if we were to have a rate law that looks like minus RA is equal to K CA to some unknown parameter alpha. So we don't know what alpha happens to be. We want to let our data tell us what alpha is supposed to be. Maybe alpha can be a non-integer, right? Maybe it could be 1.5 or the square root of 2 or something like that. If you want to do something like this, you still need to be able to integrate that rate law. Sorry, integrate that material balance. So if you were to integrate that material balance, it still looks pretty similar. You start off with dCA dt is minus K CA to the alpha. That's not a terribly difficult integral to evaluate. It's a little harder than the other ones. But if you were to integrate that, what you would end up with is CA is something that looks kind of nasty. CA0 to the 1 minus alpha minus 1 minus alpha times KT, and then all of that raised to 1 over 1 minus alpha. This is specifically for the case of alpha not being equal to 1. If alpha is equal to 1 and you put a 1 in there, you'll have a 1 over 0 in that exponent. If alpha happens to be equal to 1, you're back to the first order thing, so you'll have to integrate it the other way. But that's the general one for any alpha other than 1. This is a nonlinear expression. So this is nonlinear in T. And there's not really a good way to linearize it, to get it in a linear form of T, partly because we don't know what that, excuse me, we don't know what the exponent is. We would like to determine it. Even if there were some clever way to linearize that, let's assume that there's not any clever ways to linearize it. The process of nonlinear regression looks like the following. Suppose you plot CA as a function of time. And we're going to assume you did a really bad reaction, so you've only got 3 data points. So you've got a data point here, a data point here, and a data point here. You did it on a weekend, right? Maybe you had a little bit to drink, so your data points are pretty big. These are the experimental data points. In a nonlinear regression, what you do is you simply guess values for alpha in this particular case and guess a value for k. So let's see what color I'm going to do. We'll do green. The green points will be CA for some guessed value of alpha and k. Right? You just pick an alpha and a k out of a hat. Try to use whatever engineering judgment that you have. So for example, alpha is typically somewhere between like 0 and 3. So maybe you would pick it somewhere inside there. The k parameter, that could be a lot of different things. At any rate, we can calculate a guess for CA based on this expression. So I'm going to change this over to the green, just so that you know which one is which. Because I know you can do that in your notes pretty easily. So we can calculate CA based on a guess as a function of time. If we do that, we then put those dots somewhere near the other ones, right? We evaluate them at each of the same values of t, and we compare the two. I have deliberately drawn these as pretty bad, so they don't match up very well. We have a way to quantify how well things, quote unquote, match. The way that we quantify how well things match is we calculate the distance from this point to this point, and the distance to this point to this point, and the distance from this point to this point. We know the distances between there. The actual formula is to square those so that they're always the same. And then we keep guessing alpha and k until that distance is minimized for all of the points. The reason that different guesses can result in different results for alpha and k is because there can be multiple ways to find what are called minima in whatever that expression happens to be. The expression that we're trying to minimize, so the yellow lines over there, is usually called S. And S looks really close to what I had just described. So you take the difference between CA, actually let me color these. So CA that you have experimentally measured versus CA that you have calculated. So here's CA which was measured. This CA was the one that you had calculated from your guess. Right? That represents the distance between those 2 points. And then because we're always interested in positive values, we're not really interested in negative values, you take that quantity and you square it so that, for example, the first point and the second point would kind of cancel each other out if you were only interested in the difference between the two, because the difference in the first one would be positive and the difference in the second one would be negative, and they would cancel out. That's not good. And then you add that up for all of the points. When you have guessed alpha and k, in order to minimize that quantity, when you have minimized that S quantity by guessing alpha and k, then you have what you would consider your best estimates for alpha and k. The problem is you don't have a great way to figure out whether or not somebody else's best estimates for alpha and k are as good as yours until you quantify that a little bit more carefully. If their value of s is less than your value of s, theirs is probably better, but not necessarily. This general process that we have described here is the one that's called nonlinear regression. Nonlinear regression is the one that spreadsheet programs struggle with a little bit. They do have some features in there that can try to get you to simple forms of nonlinear regression, but they don't give you a lot of output on them. MATLAB obviously has a pretty good way to do nonlinear regression. I don't think that we're going to need it. We might bring it up tomorrow just so you can see where the tool is, because it's a very useful tool to have. And it's good not just in this class. It's good if you need it somewhere else. But this is an example of what you would do if the situation were more complicated. This is the same thing that you would do even if you were doing the differential analysis. So if you were doing this differential method and your plot of dCA dt as a function of CA didn't fit any of the standard forms and you had to do something nonlinear, you would end up doing exactly the same analysis that we've got here at the bottom where you're minimizing that S parameter. It's just you would be minimizing something else, right? Instead of CA minus CA, you would have something like DCA minus DCA. But that approach for nonlinear regression is the same. You're always minimizing something that looks like that parameter there on the bottom. The smaller that parameter gets, the better off you are. So I will just add, smaller is better. So tomorrow we'll look at an example of, we'll try to get actually through all 4 of these. I think I have an experiment from our 176 lab that I can bring in here so that we can actually look at some real data instead of me just throwing out numbers up here. And then let's see, we have no class on Monday. Hooray. So the next thing that we will do is the exam on Wednesday. So I guess that'll be a good thing to talk about tomorrow too, what to expect on the exam. Thank you all very much. I'll see you tomorrow.